next talk. We have Deb Hughes Hallett, who's a professor of mathematics, but she also has the distinction of having been the teaching assistant of our Vice President Mike Dake back at Harvard. So many years ago, when Mike was a student at Harvard, Deb was Mike's TA. So with that, if we can go ahead and start your talk, appreciate it.
Thank you very much. So first, let me explain why I'm here, because it's probably not obvious. I am a mathematician. I'm in the math department here, and I'm talking about some of the work that I've been doing here. I also teach. I have two jobs, one here and the other at Harvard, where I still teach, and I teach students of public policy. So two ends of the country, and also two very different departments. I'm here because I feel that mathematics, surprisingly, may be an outlet for outreach for a lot of your very, very important work. So I'm here to suggest this and possibly ask for collaboration and so on. Let me explain why I think this. The next several decades, I think, are potentially very fractious about water in many areas of the world. Arizona is one of them. But, for example, when I'm teaching, this is at Harvard, a group that has both people from Ethiopia and from Egypt, I have to be very careful how to manage the discussion, because the Renaissance Dam in Ethiopia threatens Egypt. And my goodness, you can tell it in the comments. China has had a huge effect on Vietnam's fisheries. Africa has had huge problems with dams. As climate change happens and more people go for renewable power, dams are important and often cause huge trouble. Turkey has dried up a lot of Iraq. Now, these also happen here. The previous speaker, thank you to her, set me up very well for thinking about Arizona. So I am suggesting, and I'll give you an example, that if you have the time and patience, and I'm happy to be a conduit, to collaborate with teachers, both in math departments at universities, as I am, and also with schools K through 12, there is a huge outlet, or potential outlet, for a lot of your important work. Now, let me first just draw a certain line in the sand. If you go to ask the mathematicians or the school teachers and say, why don't you stop teaching math and start teaching about water and so on, they'll all say no. And they're overworked and generally given enough requirements from the state or from the country that in order to fit in, what it takes to be done is that we should think about how to fit water issues into traditional curriculum. Okay. But it's not that hard to do. If you're a math teacher, for some of, I know you are not math teachers, but those of you probably have maybe children or friends or so on who have taught math. Having good applications is so important. The days of just learn it, you'll learn how to use it later, have passed. I was brought up in that era, where applications were something you did in private, but never in school. Okay. Things have changed. Kids want to know, my students here at the U of A want to know, how is this useful? And they want real answers. You are capable of producing the real answers. And I would greatly like your help. So let me look at this for just a minute. First, I'm thinking about teaching people who are not scientists like yourselves. These are people in high school, people at beginning university. First, you have to explain a little bit about what's going on with climate change and the difference between climate and weather. Okay. Yes, it's obvious to a scientist. No, it isn't obvious to an 8th grader. What is happening? Well, one thing, as Sharon talked about very eloquently, in Arizona is lack of water. And you are going to need, as you make new policies, you're going to need people to either vote for them or accept them or at least not rebel about them. And so having the general public knowing what's going on is useful. Telling them through school is actually helpful. One of the things that's useful about this is that because we are teaching math, we're, in some sense, there are some evidence against this currently, but in most cases, we are less political than most. Okay. Now, I know that math books have been banned in Florida and all kinds of complicated things have happened, but independently of that, data is data is data. And here are a couple of examples. I want to have you suggest, as Darren did beautifully, that even when you're teaching math classes, you want to start with pictures. Okay. People need to visualize what's going on. The bathtub ring is something that not everybody has seen. You start looking at the numbers, and the flow is 12 to 15, and we're using more. Okay. 20 million is bigger than 15 million. This is serious trouble. Where's the math in this? Here it comes. This is Lake Mead in 2 different years, and you can see it used to be full and it's now less full. One of the things, now here's a math piece. You might think, well, this is just a graph. Yes, it's a graph. Why does it start where it does? Well, that was when the dam was built. Why does it look like it does? It looks sort of flat. Wait a minute. It's important. Here is the same data on a different scale. You see, that's not very sophisticated, but people have to learn this stuff at some point. And you can see the drop in the second graph that you can't see in the first graph. That's useful to teach. And as a math teacher, it's great. Now, here's roughly the same thing with a line fitted through it. This is something that is in the curriculum for most kids all the way through from middle school. What is the minus 3.74 that you get out of the computer, or everybody's calculators do that? It tells you how fast the water is dropping. And as you see, the future doesn't look good. One more story. What is happening? I don't know if you're familiar with this person. Since the 70s, he's lived up in the Rockies all by himself. He built a cabin, which is on the left, and he collects snow. He went to college and then got bored with commercial life and lived up the mountains. And he's been measuring snowfall in the Rockies since the 70s. And he's quite good mathematically, so he puts it all on the web. I've had many conversations on email with him. Here is the snowfall. There it is. It looks sort of like it's dropping a bit. Here is a trend line. This is regression for economics and also from people's calculators. What is the 6.8? It's the way the snow is dropping. So part of our problem is lack of snow. It's not the only thing. And to end up, yes, I will be on time. To end up, what is going to happen in the future? One of the things that will need to be dealt with, and this is a common issue with climate change, is a particular event is often taken to be a trend. As you know, this year has been very, very wet in California, and somewhat wet even here. So here is California. This is roughly the same photograph. The water has partially replenished. There's an interesting discussion to be had with students at university and so on about what is happening next. We don't know, but please think about us in mathematics as you think about how to publicize your results. There are thousands of children in schools, millions of children in schools, and in universities all take math. we would love to collaborate. Thank you.
We have time for questions. And,
Questions? Yes.
And I love showing those different scales. That also really applies to when talking to policymakers that they're not used to looking at graphs. We forget that as academics. People aren't used to looking at graphs. And we need to have a good way to show data such as these. So any questions?
I mean, one of the problems with the COVID graphs in the last few years was that we often use logarithmic scales. I have never had more rebellions about graphs than logarithmic scales.
So I, as you were talking and talking about the water in Lake Mead, I was thinking about, okay, so what level of students are you thinking about? And I was just thinking about math problems, because Lake Mead is not a rectangle. It's like a V, and the rate of decline goes down as it goes down, but the rate of the amount of evaporation goes down. So there's all kinds of math problems you could do here, and I was curious, what level are you going at here?
The Park Service publishes depths, which is what I'm using. I mean, I just got the data and did it. I'm completely aware that lakes are not that shape, they're that shape.
No, but that's the problem for the students to figure out, right? I mean, if you're getting into like first year calculus, like what's the rate of decline if the shape's this way versus that way? I'm asking what level of students are you thinking about?
Well, I mean, you can do some of this with 6th, 7th grade. You can do more of it with 9th, 10th to 11th grade. If you look at the students coming to the U of A, we have about 7,000 a year, roughly. About a third of them, roughly, do not place into college algebra. They would not be able to interpret those lines that I have. So it's all the way through. What level it depends on the audience. The audience is very varied. One of the things we learn as mathematicians is how to adjust to the audience.
Other questions for Deb?